Properties of matter and analysis of glass lecture. Physical evidence is usually examined by a forensic scientist for identification or comparison. Identification has as its purpose the determination of the physical or chemical identity of the physical evidence with near absolute certainty. A comparison analysis determines whether or not the suspect specimen and standard or reference specimen have a common origin. Evidence that can be associated to a common source with extremely high degree of probability, such as DNA and fingerprints, is said to possess individual characteristics. Class characteristics is when the evidence can only be associated with a group and never with a single source, such as tiny fragments from a broken car window. Physical property is any aspect of an object or substance that can be measured or perceived without changing its identity, which includes both intensive and extensive properties. The chemical property of an object is evident during a chemical reaction. It's a quality that can be established only by changing a substance's chemical identity. Light exists as photons that exhibit both wave and particle properties. When visible light passes through a prism, it is dispersed into a continuous spectrum of colors. The spectrum of colors range from red to violet in the electromagnetic spectrum. Photons exhibit wave properties, and we can characterize these properties by measuring its wavelength or frequency. A wavelength is the distance between two successive crests, or one trough to the next trough. Frequency is the number of crests or troughs passing any one given point per unit of time. Density is an intensive property of matter and is equal to the mass per unit volume. Light waves travel at constant velocity until it penetrates another medium, where it is suddenly slowed and its rays bend or refract. Refraction is the bending of light waves due to a velocity change. At 25 degrees Celsius, the refractive index of water is equal to 1.333, meaning light travels 1.333 times faster in vacuum than in water. Snell's law states that the refractive index of medium 1 multiplied by the sine of the angle of incidence in medium 1 is equal to the refractive index of medium 2 multiplied the sine of the angle of incidence in medium 2. Crystalline solids have a definite geometric form due to an orderly arrangement of atoms. Many crystalline solids have two refractive indices or bifringence, also known as double refraction. Amorphous solids, on the other hand, have atoms arranged randomly throughout the solid. Glass is a hard, brittle, amorphous substance composed of silicon oxides mixed with metal oxides. The main ingredients are the formers such as silica, softeners such as sodium carbonate that lower the melting point, and stabilizers such as aluminum oxide that provide the glass better chemical durability. Main types of glass include soda lime silicate glass used in flat glass, container glass, and electric light bulbs, borosilicate glass used in lab glassware, thermometers, cookware, and sealed beam headlights. Other major types of glass include aluminosilicate glass, which can withstand higher temperatures than borosilicate glass and is used in labware, cookware, and glass fibers, as well as lead alkali silicate or leaded glass, which is used in crystal tableware. Ordinary sheet glass is made by passing molten glass through rollers. This process gives almost a flat finish, but with distortions. Ordinary sheet glass is used largely in greenhouses and garden sheds where the visual distortions do not matter. Float glass plate is named after its method of production. Molten glass is floated onto a bed of molten tin, which produces a flat and distortion-free glass. Toughened safety glass is produced by heating ordinary float glass so that it begins to soften, then rapidly cooling it after it has been cut to size and finished. This process produces glass which, if broken, breaks into small pieces without sharp edges. This is used in automotive windows and security windows. Laminated glass is made up of a sandwich of two or more sheets of glass or plastic bonded together by a flexible, normally transparent material. If the glass is cracked or broken, the flexible material is designed to hold the glass fragments in place. For the forensic scientist, comparing glass consists of finding and measuring the properties that will associate one glass fragment with another while minimizing or eliminating the possible existence of other sources. When comparing physical characteristics of glass, forensic scientists examine the density of the unknown glass. They could use the flotation method to compare densities of different glasses. In the flotation method, a glass particle is immersed in a liquid. The density of the liquid is adjusted by the addition of small amounts of an appropriate liquid until the glass chip remains suspended in the liquid medium. At this point, the glass will have the same density as the liquid medium and can be compared to other relevant pieces of glass which will remain suspended, sink, or float. To identify the refractive index of the glass, forensic scientists could use the immersion method. In the immersion method, a glass particle is immersed in liquid medium with varied refractive index until the refractive index of the liquid medium is equal to the glass particle. They look to see if the backline disappears and if there is minimum contrast between the liquid and the particle. Backline is the bright halo near the border of the particle immersed in a liquid of a different refractive index. Light passing through two substances with different refractive index produces a backline. Backline is a band or rim of light visible along grain or crystal boundary in a plane polarized light. In this image, the arrow points to the backlines. Most forensic services laboratories use a polarized light microscope to compare glass fragments collected at the crime scene. A polarized light microscope uses the optical properties of glass. A glass sample absorbs light differently depending on its orientation and polarized light. Laboratories also use the GRIM2 system, which is an automated system for identifying a glass's refractive index. The GRIM2 system uses a stepped heating stage to heat and cool liquids with refractive indices that varies with temperature. The GRIM2 system monitors a video image to measure the contrast between the glass sample and the liquid as the step heating stage is heated and or cooled until a refractive index match point is reached. Any projectile that penetrates glass produces radial fractures, which are cracks that radiate outward from the point of impact, and concentric fractures, which are cracks that encircle the point of impact. Radial cracks are formed first, commencing on the side of the glass opposite to the destructive force. Concentric cracks occur afterwards, starting on the same side as the force. High-velocity projectiles such as bullets often leave holes wider at the exit side. The direction of impact can be determined by using the 3R rule. Radial cracks form a right angle on the reverse side of the force. Successive penetrations of glass can be determined because a fracture will always terminate at an existing line of fracture. At the crime scene, if there's a remote possibility that exists that all the glass fragments may be pieced together, the crime scene technicians collect all the glass particles that can be found. If the individual fit is improbable, the evidence collector will submit all glass evidence that's found in possession of the suspect with a representative sample of the broken glass found at the crime scene. Glass fragments are packaged in solid containers to avoid further breakage. If the suspect's shoes and/or clothing is to be examined for the presence of glass fragments, those articles of clothing or shoes are individually wrapped in paper.